So today's topic is about text embeddings. We'll briefly go over what they are, how they work in a very simplified manner, and then we'll generate some ourselves. And then once we have these embeddings, it's actually quite simple to find a similarity between two embeddings. For example, Labrador Retriever and Retriever. Because these embeddings, they encapsulate the semantic, well, they capture the semantic meaning of words and sentences. So let's dig in. Before I do, don't forget to check out the members only section where all of the notebooks are posted, or on my Patreon. Check out my best products and sign up to the newsletter for my NuGet packages, the source code. And of course, don't forget to like and subscribe. So I asked my local AI to explain text embeddings. So we already kind of established that words are being transformed in numerical vectors. So a numerical representation of the word. We have already seen a technique to do so, which was bag of words, which is more like a term frequency vector. So splitting up a sentence in, well, first in words and then counting the amount of words, and that would make up the vector. So we've seen that in the naive Bayes. So this was basically simply counting creating a vector from the count of unique words in a sentence. There's some issues with that it's losing the word order. That's the first thing, because, for example, this de got counted here. So reconstructing the sentence from this representation, well, would be likely, even if you had the sentence, would likely come out wrong. You're losing the word order. And this is pretty naive. This is not capturing the context in any way. It's just taking the words, counting the words. And that's a bit similar as what I tried to do in my data prep of last video. I was just scoring similar word count without really, well, nothing else. And then we saw that American Akita and American Bulldog were getting a higher score than I would want, just because American and American was in there. So we'll have to find a better way of embedding these words, these sentences, to capture the actual meaning, not just the amount of words. Okay, so text embedding is a technique in natural language processing to represent words or text as numerical vectors called embeddings. So I've been using tokens or tokenizers, tokens, vectors, and embeddings. I've possibly used them wrong. A vector is simply a one-dimensional array of numbers, numerical vector. An embedding will have the shape of a vector, but a vector is not necessarily an embedding. And then tokens is simply splitting up a sentence in words. And as a preparation, it's preparing the inputs before going into a model, a BERT model, for example. Anyhow, these vectors are designed to capture semantic meaning of words that can be used by various NLP tasks such as classification, clustering, similarity, measurement. Then there's a few advantages for embeddings over other techniques, and scalability being one. As the vocabulary size grows, the number of dimensions increases exponentially, making it difficult to scale for large text or data sets. Because that bag of words example, you would basically, the vector size would grow the more sentences, the more unique words it encounters. So because every unique word is getting a position, a place in the vector, so it would expand with the amount of unique words. So then there's several text embedding models, which is Word2Vec. Word2Vec generates word embeddings by predicting words based on their context. It uses two main techniques: continuous bag of words, which is a probably more advanced bag of words, predicts a target word given its surrounding context words. So this is already a bit more sophisticated than simply term frequencies based than just counting the unique words. Okay. Word2Vec models are trained to minimize the difference between predicted and actual word vectors. The resulting embeddings capture semantic relationships between words, such as synonyms, antonyms, and analogies. Then GLOVE, another one you'll encounter. Global word representation model that captures both local and global features of words. It uses a matrix factorization technique to decompose the co-occurrence matrix into two lower dimensional matrices, one for words and one for context. Okay, cool. So we've seen matrix factorization briefly on the recommendation engines, in which they decomposed the user item matrix in a users matrix and an items matrix or something. GLOVE embeddings are computed by multiplying word matrix with context matrix, resulting in high-quality vector representations of words. FastText provides efficient implementations of various text embedding models, including Word2Vec and GLOVE. It also introduces subword embeddings, which represent words as a combination of smaller subwords, word pieces. Subword embeddings can be more effective for out-of-vocabulary words or words with multiple meanings. Then BERT, which we are using a BERT-based architecture for our similarity, sentence similarity, and named entity recognition. So bidirectional encoder representations from transformers is a pre-trained language model that uses multi-head self-attention mechanisms, maybe we'll ever learn more about that, to generate contextualized word embeddings. These embeddings are called sentence embeddings. So to generate contextualized word embeddings, these are called sentence embeddings because they capture the meaning of an entire sentence. BERT has achieved state-of-the-art results on various NLP tasks, including question answering, sentiment analysis, and text classification. Then we have a variation, Roberta. It's a variant of BERT that uses a different training objective and achieves even better performance than BERT on many tasks. Although when I did some Googling, this is trained mostly on English vocabulary, or was that GPT-2? I should check. For multilingual embeddings, we'll have to look for different models. Then some others: Doc2Vec, word embeddings for documents, and sentence BERT, sentence embeddings. Then multilingual models, which I might be interested in for those translated dog breeds. We'll see why below when we're doing the exercise. We'll see, for example, that Dogo Argentino and its Dutch variant, Dutch translation, literal, Argentijnse dog, doesn't have a great similarity score because the embeddings, it's lacking since the model that we use below to generate embeddings is not properly trained on all of these, on other languages, let's say. I think we're using Llama 3.1, which can do English, Portuguese, and other languages, Spanish, the more common, the most spoken languages, but on Dutch, for example, it fails. It's not that good, let's say. Okay, then some multilingual text embedding models: Muse, Polyglot, FastText Multilingual, MADA, textual question answering. But then we're more interested maybe in the BERT-based ones. MBERT. Couldn't find this model anymore. Maybe a few years ago I did use it for something. Roberta. Okay. And then this XLM, which I can find, is trained on 100 different languages. So maybe this may be interesting to use in the future. Or like an mRoberta, since we're already using this architecture with TorchSharp and ML.NET. Okay. So this is where I asked my local LLM to explain how embeddings work, but to simplify the explanation. So let's get into it. Imagine you have a huge library and millions of books. Each book has its own unique title, author, and content. Now imagine trying to find all the books related to a specific topic like space exploration. A traditional search would, when the user enters a query space exploration, the system would typically rely on keywords or phrases within each book's metadata, title, summary, and so on. It would then match these keywords with your search term and return relevant results. This has limitations. Books may contain irrelevant information, irrelevant non-essential information we call noise, or use different words to describe the same concept, like synonyms and so on. Oversimplification, keywords don't capture the nuances of a text. They're often too broad or too specific. Text embeddings aim to solve these issues by transforming each book's content into a numerical representation called an embedding, or a vector. Which captures it's called an embedding because it's a vector containing the semantic meaning of the book's content. And that contains the essence of the book's content, let's say in a numeric format that summarizes the text in a compact and structured way. Each word in the library is represented as a point in a high-dimensional space. Okay, we'll need some visuals to do that. I have linked some links below, videos in which you can visually gain an understanding of vector spaces, these high-dimensional spaces where each vector is represented as a point. The distance between these points represents how similar or dissimilar their meanings are. Text embeddings help us find books based on their meaning, not just the keywords. So the embedding is a vector that captures context. The surrounding words and phrases influence the embedding. Preserves the meaning. Similar concepts are represented by close vectors in the space. With embeddings, when you search for space exploration, the system can find relevant books based on their content's similarity to your query, even if they use different keywords or phrasing. So the semantic meaning. That's cool, eh? Text embeddings bring several benefits. Improved relevance. The search results are more accurate and relevant. Noise reduction. Irrelevant information is reduced or eliminated. Efficient search. Embeddings enable faster search queries by leveraging pre-computed vectors. Yeah, that we have to do below. So, in the context of my example, text embeddings help find similarities between texts like Togo Argentino and its translations by comparing their semantic meaning rather than just the keywords. Ooh. So some links to understand it better. Okay. YouTube videos and blog posts, more in depth. So I'm going to simply pass I'm going to generate embeddings using a pre-trained model, my local LLM 3.1. I'm just going to pass the text to Argentino, and it's going to generate a numeric representation containing the semantic meaning of that Togo Argentino word. As you can see, it has, I think the size is about 4096 numeric values. Let me give a quick shout out on how I came to the idea to do this using the local llama. The codeman.net is Stefan Jokic or Tokic. well, it came in my email mailbox. I subscribed to his newsletter, and he basically showed me that using Ollama's API, which we have already installed, we can simply call the API/embeddings endpoint to generate these embeddings based on, if we just pass the text we want to generate an embedding for. Using Mistral, but I'm going to be using Llama 3.1. If you don't have that model, if you don't have that installed, you can follow my videos, your free AI assistant, Llama 3 local setup guide, and then the following video, which shows you how to run it using your GPU. This is very interesting that you can do that. There's other ways, but let's start like that. So I'd be opening my Docker, running my Ollama local Llama 3.1. Since we're doing a post request, I'm going to use either Postman, or I already included embeddings generation like .http. If you have the extension, you can probably run this. Basically, post to localhost, the port API/embeddings, application JSON, passing the model, and then the prompt for which we want to generate the embedding for. And then it's giving me that embedding contains the semantic meaning of Japanese Akita. So that's how I generated all of these embeddings. For Dojo Argentino, then a different spelling, maybe a misspelling, Dojo Argentino, then a Dutch translation, Argentijnse Doch. Then I wanted to try to see how different this is lowercase, this isn't, how different these embeddings would be. Then just retriever, which could be like our search query, then golden retriever, Labrador retriever, flat-coated retriever, flat-coated retriever, which is slight variation in spelling, Toller retriever, and we want to measure their similarity. How? We can use either, there's two possibilities, cosine similarity, which measures the angle between two vectors. You can see that in the videos I linked above. And there, it's recommended to use this. And then there's another possibility. So, well, this is how to calculate cosine similarity. This is AI generated code. It seems to be working fine, but should maybe double check. We could also use TorchSharp. This is a visual representation of how it works. Angle, the distance between two embeddings. And then apple and banana are further away from cat and dog. Cat and dog are similar, apple and dog are not similar. Produced by this person. Okay, cosine similarity, then there's the dot product, as they call it. Well, the entire formula is here. And how to get to a similarity score. Okay, then there's Euclidean distance, which we've seen already, but it's not the recommended formula to. This is basically measures the straight line distance between 2 points, which is a good choice when you want to measure a dissimilarity distance. So we now used our Llama or LLM, local LLM, to generate these embeddings, and now we're going to measure the cosine similarity. There are, so like I already mentioned, we can train BERT-based models to generate these vectors, or use Word2Vec or other models, which are pre-trained models, I meant. Because some models, like we saw with the multilingual ones, may perform better on, for example, this Dojo Argentino versus Argentijnse Doch. Similarity is only 0.37. The Llama 3.1 model is not too great using generating content for the Dutch language. So that's likely a explanation for that. So now, similarity between the embeddings Dojo Argentino and I assume a misspelling is pretty high, but I would hope for like a 98% 98% similar or something, but still pretty good. Then Dogo Argentino and Argentijnse Dog, which is a bit the similar thing what I did. Just 1G and then the Dutch translation. And I'll see below why it's that low. It's not just the translation that the model that I'm using may not be well trained on Dutch language, but it's also the word order. So we've got Argentijnse Dog, and then the original name starts with Dogo and then Argentino. So there's a difference there. Then I tried uppercasing. Seems to have a slightly better similarity. So perhaps the casing seems to matter. Then I tried to achieve something more like a search query, like a retriever and golden retriever, which is 66. Flat code versus flat coded retriever, 96. That's pretty good. It's just it's possible that the embedding doesn't really, may even throw away the ed, but I'm not quite sure how it pre-processes the text to have bring it down to a base form or something. Like ing, if words ending in ing, sometimes it kind of just gets reverted to its base form or verb. The Labrador Retriever and Toller Retriever, 86. That's pretty good. Although maybe I don't want this to be too high to still know that these are different breeds. Then Labrador Retriever versus Dogo Argentino. This is still higher than I would like for my use case, but it does make sense, both dog breeds. So it's going to be pretty close compared to, for example, Apple and Labrador. We can see that below. So could you explain why the cosine similarity is low between Dogo Argentino and Argentijnse Dog? And then it answered because, well, first of all, see, my llama tries to correct my spelling, but I don't think that's the correct spelling. Argentijnse Dog, which may be more the German or the old Dutch spelling. Cosine similarity. So that's not good. Might be low because the language models generating these embeddings are sensitive to the nuances of the word order. So that's what I said before, Argentijnse Dog instead of Dogo Argentino. So to illustrate this point, consider that even Dogo Argentino and Argentijnse Dog are essentially the same concept, a breed of dog. Their word order and language nuances can lead to distinct embedding representation. One possible solution is to use a multilingual model or fine-tune an English model on Dutch text data. Another strategy is to experiment with different models like multilingual, XLM, MBERT, and so on, using a model specifically trained on dog-related text, so on dog breeds and so on. Multiple language might yield a better result. This is more like what we call fine-tuning. It's using a more general model and then training it on specifically on domain-specific text or language. Then I've got American Akita, American Bulldog, Akita Inu, Akita, Japanese Akita. We want to see the similarities between these because in my naive word count example, American Akita and American Bulldog had some similarity simply because of the word American. Let's see how this performs in here. So American Akita versus American Bulldog, still 0.85. It's even a better score than my naive word counter gave. And that's only slightly lower than American Akita versus Akita Inu. So this is a bit worrisome. Although if we put this in the mix, let's say we built a semantic search and we wanted to find American Akita, it's going to show me Akita Inu before American Bulldog. We're likely interested in the most similar or the top 3 most similar. This could be in the top 3, unfortunately, if it's got such a high score. Because American Akita and just Akita seems to perform way lower. Not even 70. Akita Inu versus Akita, 66, 67. That's not that good. We would almost think that the word American impacts the score more than the word Akita. Then American Akita and Japanese Akita, that gets a really high one. So this would be my number 1 in the semantic search, and then we would have a Akita Inu, and then maybe the American Bulldog. And then Dogo Argentino versus American Bulldog, just to know, is a 0.63. And then you likely have to decide if, let's say, the top result is only 0.7, do we want to propose that as the most similar, or cut it off, or just not go for results higher than 80? So then followed by some code to generate these embeddings yourself using C#, the HTTP client. So HTTP, we're going to get an embeddings response, only the embedding, but I'm gonna attach the input text so we know which, well, we can have some kind of mapping. So to this endpoint, using this model, simply doing an HTTP client call, but without our extensions, we have to use a post async and string pass string content with the serialized request body, which contains the model, and the prompt, which is just the input text. I put it to lower just to not have too much dissimilarity between something being uppercased and something being lowercased. And then we just return the embedding response and attach the input text before we return it. Then how to use this? Yeah, just put it quickly in a for loop. We are going to generate embeddings for these. So just looping the breed names, calling this API endpoint. So the first embedding.length is 4096. I just wrote this function to mimic the semantic search. We're going to get a top 3 of most similar embeddings. So let's say we pass a search query, then we compare them to all the embeddings, measure the cosine similarity, search query and result, and then we order them descending. So for all these, retriever, Akita, Pitbull, flat-coded retriever, I added American car and American pie and coffee americano just to see how that performs against American bulldog. Okay, let's have a look. So we're basically doing, for retriever, the top cosine similarities. So we've got a 0.73, which is not that high between retriever and flat-code retriever, but this is way better than our sentence similarity results. Then we have almost 70 retriever and taller retriever, Labrador retriever. So at least all our retrievers are in the top 3. Then we have a way lower for American Bulldog and American Akita. So that's a pretty good result. So this is a subset of my dog breed dataset. We generated all the embeddings for that. And now we're mimicking search queries, generating embeddings for these, and then comparing them to our so-called subset of our database to mimic the semantic search. Okay, Akita, Japanese Akita, almost 80, that's pretty good. Then we have American Akita and Akita Inu. So that's a result I really like as well, although it's a bit on the lower end in terms of scores. At least we've got all our Akitas at the top. And then it's Flatcode and Dogo Argentino. What sometimes baffles me is that the results are not that far off. Well, it's a completely different thing. It's a dog breed, it's a dog, okay, but for the rest. Let's see, then Pitbull. It's gonna say Flatcoat, Labrador, American Bulldog, American Akita, and Dogo Argentino. All pretty high, well, all almost, yeah, between 60 and 70. I don't have any Pitbull breeds or in the data. So yeah, We could say, as humans, we could say maybe Dogo Argentino or American Bulldog should be closer, so should be at the top. But yeah, that's maybe a use case for fine-tuning a model on dog breeds, and maybe have some other characteristics taken into account. Okay, so then I have flat-coated retriever. I left out the dash, and I said coated, which is likely not... don't think it's the official name, but anyhow. Then we've got the Labrador, got a higher similarity than the actual flat-coat retriever. So that's not great. Maybe flat-coat is wrong, who knows? But yeah. Then flat-coated with Toller, still very high. Flat-coat retriever with American Bulldog, that's the bullshit I find. It's just 0.01 lower than Toller retriever. Well, it's a completely different thing. And then with American Akita, it's still pretty high. Although the retriever breeds, they're likely Canadian or something. Maybe that's... and dog breeds and so on. Let's see. Okay, so now just to see if American, what the weight of the American is. American Bulldog and American Car is only 0.44, so that's, well, it's good that it's bad, because we wouldn't, Car is something completely different than a dog breed. 4.42, American Car and flat-coat retriever. Okay, American Car, American Akita, still low. Labrador retriever, American Car, low. Japanese Akita, even lower. American Pie, American Akita, all low scores, that's good. Coffee Americano, let's see, 59 is a bit higher. For some reason, coffee closer than to a dog than a car, okay. 0.57, I would assume maybe this is on the top, because, yeah, maybe the language. Okay, that's all there is to it. So now we can choose. So now we have these embeddings, and we can fairly simply compare them to other embeddings to see to find the similarity. So we could cluster them and probably find clusters with the most similar embeddings. We could even, if necessary, which I don't think it's necessary, we could train another model to simply classify based on these embeddings. I once did that for a face recognition app, also because I didn't know any better at the time, but basically August 97%. And this used, the embeddings were generated by Face API.js, which basically was a trained model to find the essence of human faces and how they differ. So this embedding of my face, well, if I take 10 pictures of my face, those embeddings would be quite similar compared to 10 pictures of somebody else's face. And then what I did is I trained a feed-forward, a simple neural network on that, simply to classify the label and the embedding. But yeah, you could have also just taken a picture of myself or somebody else and then looked for the most similar embeddings. Don't need to train another model on that, but I did anyway. One of my first proof of concepts, let's say, long time ago with TensorFlow.js, Face API.js, so on. So I did some training using TensorBoard, TensorFlow. We should really have something like this in Blazor. Maybe I'll make one. The training, so we've got a very good high accuracy. But yeah, then again, we might, this model is not really necessary. And then yeah, it had like a 88% accuracy, so it was fairly capable of detecting people based on their face. Just to say, I could likely, well, I wouldn't do it with this Llama model, since the Dutch language, it's not performing too well on the Dutch language, and there would be too much dissimilarity between Argentijnse dog and Dogo Argentino, for example, so that wouldn't fit my use case too much. So I might try another model, which multilingual one, And we can put some links down below. I think this one, Semantic Search. We could do it. Here's somebody who's is showing how to train your own model using DistillBERT is a different model. With MS Marco DistillBERT base v3 is a variant of the DistillBERT, was originally designed for English language tasks. However, it was fine-tuned on the MS Marco dataset, which contains a large corpus of web documents in multiple languages. As a result, while the original DistillBERT model is not multilingual, this variant has been adapted to work with multiple languages. But it's still English-centric, and that's, for our dog breed case, that's not the end of the world, because we only have a few translations. Most dog breeds are kind of in Dutch, or often, because they come from England or the US, we likely use them in the same manner, in the same language. English-centric, despite being fine-tuned on multi-language data, this model still prioritizes English as its primary language, so that's not a big issue, I think. But if we want to go for truly multilingual models, then there's BERT-based multilingual, there's XLM BERT-based, might be interesting, and DistillBERT multilingual case, this might also be interesting for our use case. If you're just working with English text, don't bother training different models. If you don't want to rely on your local LLM to generate embeddings, you could try the Roberta model. Well, use the Roberta model or a GPT-2 model, GPT-2 to generate embeddings and so on. To take it a step further, how to implement RAG, that's Stefan's blog post, which I received in my mailbox and I briefly showed. He goes further, not only to generate the embeddings, but also to store those embeddings, because we don't want to generate those each time we do a search query, a search for semantic search. So we need to store that, and for that he uses PostgreSQL. So that's taking it a step further. That semantic search is basically enough for me now. So that was this coded blog post I linked here at the bottom with the GitHub. And then fine-tuning text embeddings for domain-specific semantic search, how to fine-tune those BERT models on your data. This is the ONNX documentation. So basically showing you how to use a BERT model in C# using the ONNX runtime, which we all are already using with ML.NET, or in the YOLO videos that I made. YOLO v8, we're using ONNX to load the YOLO model that we exported using Python-oriented bounding box detection. Very cool, because as you may know, Hugging Face is full of very interesting models for OCR, for anything, for semantic search even. All those BERT-based models you can find there, multilinguals and more. So you can plug that into your C#.NET projects. Okay, so the code of the notebooks will be dropped on my members only, which you can access after becoming a member, or you can get it from my Patreon after becoming a member, or when you're already a member. Don't forget to check out my best products, and if you want some free source code, you can subscribe to my newsletter, the source code of my NuGet packages.